of fluids, environmental. So I have brought before you a very important and limited applications which are relevant to us, because if we see the applications of nanotechnology and nanofluids that are also exist and present in electronics also, and in many engineering streams. Since the research field nowadays is interdisciplinary, we can study any kind of problems wherever it present, in whatever form it is, and we can give our concrete solution in terms of any technology. Nowadays we learn so many things in our life, but the question comes, what is next? Because whatever basics is there, chemical engineering suppose, chemical technology is suppose, chemistry is suppose, so many books we are referring, the question is what is next. Next is, what is the advancement in your field? That is very important. And the advancement is nothing but the nanotechnology, membrane technology, ionic liquids, some computational engineering, process engineering, and many others, right? So what is next is very important. If we are working on the next, then automatically our research have a value in the market in terms the research society and the research fields. So next slide, please. Before taking you to the applications, my presentation outline will be introduction to nanotechnology, first of all, because to discuss nanofluids, we should know what is nanotechnology. That is very important and vital. So I have added few of the things or slides which are very important to know to everyone, from whichever field he comes from. He should know clearly and very easily that what is nanotechnology. And after that, I will explain what is nanofluid. That is very important. Historical evidences of nanotechnology, applications of nanotechnology, because we are reinventing the wheel back. Which wheel backs? Nature's wheel back, right? Because whatever we see, why it is exist, what is the technology behind. So we found few traces, few of the things in nature's wheel, and that nature's wheel we are reinventing back again to carry out our research in terms of nanotechnology. And that is why we need to critically see what are the historical evidences of nanotechnology, and that we are reinventing back in terms of nature. Then applications of nanotechnology, my group, my research scholars have worked on some applications as far as nanofluids are concerned that I'm going to discuss. Then literature based upon our publication and conclusion. Next, please. Yeah, if you could see, the screen is so dynamic. All of we know that nano. So what is nano? That is very important. So the screen, I think everybody is visible. I think so. So why nano should be worry about, and why? This is very important. Nano के बारे में हमें क्यों worry करना चाहिए और कैसे करना चाहिए? Why should we worry about nano and why? So if you see the scales, so three types of scales are there. Time scale is there, weight scale is there, and length scale is there. Next. As far as time scale is concerned, next slide. As far as time scale is concerned, we can go from nano to yocto. That means 10 raised to minus 9 to 10 raised to minus 24, right? Next. If you see this particular scale of time, it can go up to atto, right? That means from 10 raised to minus 9 to 10 raised to minus 18, it can go. But how quickly we can do the things that this scale particular is indicating. Next slide, please. In weight scale, if you see the weight scale is also from nano to the yocto, just next, just give a tap. It goes from nano, that is 10 raised to minus 9, to zepto. That means lighter component, lighter material. Now, got my point out. Now we are going from kg to gram or something like that. It is lighter. The material becomes lighter, right? And we have the lighter material flexibility till this particular scale of Jepto, that is 10 raised to minus 21. Next slide, please. So in length scale, if you see, because these are three scales which are very, very important as far as nano and beyond nano we wanted to go. So as far as length is concerned, length means the diameter in terms of I'm talking about. Next, please, just give it a tap. It goes from 10 raised to minus 9 to 10 raised to minus 10, and again it's written back to 10 raised to minus 9. It means what? As far as any material, whichever is made of stone or human living traces, balloon, etc., etc., construction material, any material, the material molecule is of 10 raised to minus 9 meter, and atoms, the end size or length of the atom is 10 raised to minus 10, and everything is made up of a atom. So this particular scale, which is ranging from 10 raised to minus 9 to 10 raised to minus 10, after going towards 10 raised to minus 10, it is again comes back to 10 raised to minus 9. It means the length scale, if shape changes, if size changes, if diameter changes, you can say if length changes, the properties are changes because structural changes. If properties of property changes as far as the material is concerned, that is physical and chemical property. Property also changes of the material. So down, if you see the nanoparticles supposed to be referred as the particle which is in the range of 1 to 100 nanometer. At the bottom, if you see this red, and there you can see that one nanoparticle is referred when it is in the range of 1 to 100 nanometer. Next, then atom is there in terms of angstrom, that is finer to the nano also, because it is 10 raised to minus 10 meters. Next, and then finer than the nano, coarser than the nano, then IgG, viruses, bacteria, then some of the cells, nuclear cells, and red blood cells exist that are coarser than the nano and finer than the nano. If any material will be there, it is exists in the form of atom, and that is 10 raised to minus 10 meters. Next slide. Eigenweng in 1999 proposed that a magical point on the length scale for this is the point where the smallest man-made devices meets the atoms and molecule of the natural world, and this fellow has indirectly defined the terminology of the nanotechnology. He stated, once again I'm repeating, the magical point on the length scale for this is the point where the smallest man-made devices meets the atoms and molecules of the natural world. Next slide. This particular study is very, very funny, as well as very important to know the power of 10, and it is available on the Google also. I deliberately brought before you to know what is the power of 10, right? This particular man is enjoying the picnic and laying his hand on his chest, and he's enjoying the picnic. He's just enjoying laying on the floor, and this particular image is captured from 1 meter. Next slide, please. Now we are going towards a distance wise ahead. So this particular image is captured 10 meter from 10 meter of distance. Next slide. Then 100 meter, you can see a very small, that fellow is observing to us. Next. Then magnify it. Now just concentrate it, his closer look at the hands of the man, and magnify the things. Magnify means we have to go into deeper and deeper and magnify the scale into a negative direction. That is from 10 centimeter, 10 raised to minus 1 meter. Okay. So we can see a closer look at the hand of the man which is sleeping at the picnic. Next slide. Then at 10 raised to minus 2 meter, 1 centimeter, we see the crevices in the hands of the skin of the man. Next slide. Then at around 10 raised to minus 3 meter and 1 mm, we just see skin is, we just see below the skin of the man hands. Next. At 100 micrometer, that is 10 to minus 4 meter, we see the thin layer of skin just above the capillaries. Next slide. Now, at around 10 to minus 5 meter or 10 micrometer, we see inside the capillary vessel a lymphocyte, a white blood cells are visible. Next slide. At around 10 to minus 6 meter or 1 micrometer, we see a protective membrane inside the lymphocyte, which encases the cell's nucleus, right? So this is the magic. When we are going towards finer and finer and finer, we can see, which is not, can be visible at ordinary scale, that we can see when we go towards a finer and finer scale and length. Next slide. At around 10 to minus 7 meter, that is 100 nanometer. Now, this comes to a range of nano. The nanoparticle is the particle which having a range possesses in between 1 to 100 nanometer, and this is 100 nanometer. Okay, so we cannot say any material which are beyond 100 nanometer. It is not a nanometer. Talk to about, try to understand, the concept behind. So we see the coiled DNA strands within cells nucleus. Now see the importance of scale. We see the coiled DNA strands within the cell's nucleus. From that man's hand, which was previously, looks very classical one, now a very in nanometric range scale, or the finer and finer or higher magnification. With higher magnification, if we see a special part of the man's hands, we can see the coiled DNA strands within the cell's nucleus. Next slide. At around 10 to minus 8 meter and 100 nanometer, we can see the shape, how the shape of our DNA strands looks. It's a double helix shape of that particular man's hands inside. Next slide. At around 10 to minus 9 meter and 1 nanometer, we see our molecular building blocks. A carbon atoms bonded to 3 hydrogen atoms, and that is our origin basically. So you see, when we are ranging from the scale from micro to the nano and finer to the finer with higher magnification, if we go, we can see how it is composed. If we can see, we can tackle. If we can't see, we can't tackle. So nowadays, if we see, then tackling equipments, how to tackle, how to go for, medical field is very much become strengthened due to this, because we can see at finer level, we can see at higher magnification that what is the shape and size of that particular material, and that is very important to tackle. Next slide. Now, as far as understanding of size is concerned, it's the finer is atomic, then molecular, then nanoscopic, then viral, then microbial, then cellular. Next slide. So from ants to the atoms, size varies basically. Every material possesses its own size, and that size matters because of that size only, or you can say length of that particular material, whether it is living material or non-living material, its property changes. So you can see from red ants to the hydrogen atoms, various properties are exist, and different properties are exist because structure changes. Next slide. As per understanding of the definition is concerned, at least one dimension, एक कोई भी dimension should be in the range of 1 to 100 nanometer. So size of sugar molecule is around 1 nanometer. Very dangerous. Sugar consumption is very dangerous because it reacts with protein very fast, and it may cause a cancer. So sugar is very dangerous molecule. Its size, you can say length of one molecule is 1 nanometer. 10 hydrogen atoms laid side by side combines together 1 nanometer. Very important. That is why hydrogen is very important element. One bacteria 10 to 3 nanometers, that is 1 micrometer, and nanoworld is the ultimate building block of matter, sets a hard limit to shrinkage. Next slide. Richard Feynman, he was a great physicist basically, and he has given us the idea that what is nanotechnology. So while presenting in his talk, he talks about there are plenty of room at the bottom. वो जब बोल रहे थे एक हॉल में असेंबली में उनके पीएचडी वाइवा को डिफेंड कर रहे थे, वो he stated there are plenty of room at the bottom, so people laugh at him. And what he's talking about? He was talking about nanotechnology. He was talking about atoms and molecules present in that particular hall, and each and every atoms and molecules he was talking about rooms. So number of atoms there in the room, number of molecules in that particular rooms, he referred it as one room, and that is why he talked about there are plenty of room at the bottom. And this was the lecture given by physicist Richard Feynman at an American Physical Society meeting at Caltech on December 29, 1959. And Feynman considered the possibility of direct manipulation. Direct manipulation means atom by atom precisely, or molecule by molecule precisely, we can manipulate as per our convenience as a more powerful form of synthetic chemistry than those used at that particular time. So the principles of physics, as far as he can see, he told, I can see, do not speak against the possibility of maneuvering things atom by atoms. It means atom by atoms manually मूव करना, मैन्यूरिंग करना, उसको हमारे हिसाब से टैकल करना, बनाना is really a possible because it's atom and molecule when we can see. Next slide. Eric Dexter later stated that nanotechnology is the principle of atom manipulation, atom by atom, through control of the structure. So structure can be controlled at of matter at molecular level, and it entails the ability to build molecular system with atom by atom precision, yielding a variety of nanomachines. And nowadays we can see, atomic force microscopy, a scanner tip is made up of a carbon nanotubes, scanning electron microscopy, Raman spectra, and many scanning, the machines have the nano machines equipped with it. And this is stated by the Eric Dexter. Next. So that time, the postulation of Richard Feynman that maneuvering of atom by atom is possible. So this is possible by that time Don Eigler. He was a scientist at IBM California in 1989. He becomes the first person to move the atoms by atoms together, and he prepared a IBM logo by combining 35 xenon atoms he put together, and still this IBM logo is exist on their office. And now also we can see this logo at every machines of this IBM systems. Next slide. So is this nanotechnology? Is this only the nanotechnology? No. Next. Is nanoscience just seeing and moving really small things? Yes, but it is also a whole lot more. Properties of material change at the nanoscale. Next. Nanotechnology is concerned with developing the tools, because if we are talking about the technology, we should also be fair enough or concerned enough to develop the tools, to see it, okay, to have its characterization, that how will be the property of it, what will be the shape and size of it, how it will look, and how to manipulate, to do that particular one characterization is very, very important. So nanotechnology is concerned with developing the tools also for characterization and manipulation of the material on nanoscale level, that is 1 to 100 nanometer, and exploiting these tools. These tools को exploit करना for the development of a new product and processes is also a part of nanotechnology. Next. As far as the definitions are concerned, most of we people are ignore basically that what is the difference between this particular terminology, and these are very important terminology. Now we talked about nanostructure, and nanostructure, but we generally confused while stating the nanostructure. So what is nanostructure? Based on their geometrical dimensions, with reference to an external surfaces system or substrates, the narrow definition of nanostructure, to whom we call a nanostructure, is at least two of its dimensions are below 100 nanometer. कोई भी मटेरियल का 3 डायमेंशन में से 2 डायमेंशंस should be below 100 nanometer. We can call that particular substrate or material or any system as a nanostructure. And the extended definition is at least 1 dimensions below 100 nanometer, and a second dimensions below 1 micrometer can be referred to as a nanostructure. Next slide. Now, what is nano devices? Everybody's talked about nano devices. Was the Tata car nano car was the nano devices? No. Just the name, he has referred name as a nano, but no component of that particular car was nano. So what is nano devices? At least one functional component, जो component functional करता हो, is a nanostructure. वो nano structure का होना चाहिए. इसका मतलब ये है, you have to also see back or look back to the definition of nanostructure. At least one functional component should be a nanostructure, and nanostructure definition you know this now. It may be called as a nano device. And we also, you know, lightly referred anybody that this is nano system. You know what is nano system basically? So consists of several nano devices. Means this nano devices which have at least one functional component is a nanostructure that are of importance of the for the functioning of the whole system. Whole system functioning करने के लिए it should consist of a several nano devices. Then we can call that particular system as a nano system. Next, that this slide we have already discussed. So we have a scale ranging from nano to micro to milli, and many materials are falling in this particular scale, and these materials are this one. We have already seen this slide. Next slide. Yeah, we can see from historical evidences. I have already explained you that we are reinventing wheel of the nature back. That this particular technology, Lysergus cup, that was invented from Rome, is an example of dichroic glass, colloidal gold and silver in the glass, which has uh, uh, there on the glass, to look opaque green when lit from the outside. but बाहर से अगर उसके ऊपर लाइट आपने डाला तो वो ग्रीन नजर आता था, but translucent, very red when light shines through inside. So this is a magic, because gold and silver nanoparticles present in the glass cause an ancient object to change color when subjected to different angles of light. So opaque property is very, very important, and that was initiated, and that was already, exist that time in 4th century of the Rome. Here you can see the from 6th to 15th centuries, vibrant stained glass windows were there in European cathedrals. Owed their rich colors to nanoparticles of gold chloride and other metal oxides and chlorides. So gold nanoparticles also acted as photocatalytic air purifier, right? This is very important. So nowadays we can see the various colors on peacock feathers, butterfly wings. Can we really, made or synthesis at our laboratory? No, that is because of opticality, bandwidth, phenomena, bandgap phenomena, and because of that, melanin rods are arranged in a systematically there on the peacock wings, on feathers are arranged in a systematic way so as to maintain the band gap. And when the light comes on that particular feather, it exists, various beautiful colors to us, just like a photonic crystal, which is systematically arranged and guided a photon, that is light, that systematically pass through it and reflect us a various colors. Next slide. So there are various types of nanoparticles that are naturally occurring. Second, incidental nanoparticle, and third is engineered, right? So naturally obtained nanoparticles, our sea spray you must have seen. So that is also called as aerosol particles, which are formed from the oceans, right? Oceans में जब आप जाओगे तो sea spray or aerosol particles are there that are naturally occurring. That are also nanoparticles, naturally occurring, particles. Then viruses are naturally occurring. Volcanic ash, fine sands. So these are some of the examples that nature gives us some particles which are also in the range or around the range of 10 to minus 9 meter. Next slide. Some incidental nanoparticles. So from cooking smoke, produced as a result of byproduct of process. That is byproduct of combustion, industrial manufacturing, and other human activities which we generally used to carry out, day-to-day life, can emit a incidental nanoparticle, because smoke, whatever smoke, In our old days, our mother used to cook, you know, by using the woods, and that whatever smoke is coming out, that was also a nanoparticle. Smoke means, this vehicle smoke. I'm talking about coal mining fly ash, industrial effluents that are incidental nanoparticles, and engineered nanoparticles, what we synthesized in the laboratory to control shape and size of the nanoparticle. So intentionally produced. We are intentionally produced, no, because of the application specific. Depending upon the application, we are producing nanoparticles as per their property. What property we need, that we have to define as per that particular property, and we have to synthesize nanoparticle applying that is why it is referred to as engineered particle, intentionally produced material that has a size in 1, 2, or 3 dimensions of typically between 1 to 100 nanometer, very precisely controlled size, shapes, and compositions. This image is captured by FACM, may be referred to as engineered nanoparticles. Next slide. So what are the key features of nanotechnology? More surface area to volume ratio, that we know. That means surface area, if suppose you can see the surface area 27 centimeter height, then 1 mm, then 1 nanometer. So surface area to volume ratio is increased. Okay. If we go from higher to the, micro to the nano level, surface area to volume ratio increases. And depending upon this particular property, we can synthesize catalyst, which will provide more surface area for the reaction to occur, and which will increase the rate of the reaction. So likewise, wherever it is possible, as far as this particular application is concerned, so the material is giving you more surface area for the reaction zone, and using various combination in honeycomb also it is possible that provide more surface area to volume ratio to the reaction zone and have increased rate of reaction. So in that particular case, it is to us, where to use this particular all features of the nanoparticle, and in which case that is the skill of the scientist and academician. The higher the surface to volume ratio, that is called aspect ratio, the material are stronger, stable, and durable. Materials may change optical, electrical, physical, chemical, and biological properties at the nanoscale level. Because structure changes, property changes. So it's optical, electrical, physical, and chemical. These properties are basically changes because of their structure changes. Makes biological and chemical reactions easier. Can attach various reactor groups to increase the chemical affinity towards the target. Next slide. These are the real-time example basically. We can skip out this example. Nowadays, anti-sunscreen lotions, all sunscreen lotion is having a, some formula, okay? That formula is TFM. That formula is about number of nanoparticles, sun protection formula, okay? SPF. Whatever SPF you can see on sunscreens, lotions, that is sun protection formula. And that formula is nothing but the number of nanoparticles added to that particular cream. Okay, that can help us to pass light to that particular skin, and it will reduce the light. Okay, avoid darkness of our skin. So this is the SPF means what? This is written SPF 50. It means 50 number of nanoparticles added to that particular sunscreen lotion. 25 SPF, 25 number of nanoparticles added, like that. So titanium oxide, self-cleaning gases, aluminum silicates, scratch resistance coatings. So likewise, many examples you must have seen in the real production scenarios. Next slide. Nowadays, nanotechnology market, if you see market in the year of 2020, it was very low. But now if you see the market in terms of various field, electronics, energy, chemical manufacturing, aerospace and defense, healthcare, others. So nowadays, a lot of applications in terms of nanotechnology and a lot of involvement of the, uh, as far as the value of the market is concerned, and the money is involved, that are involved in the research of nanotechnology and its production further. Next slide. Now, this particular, we will discuss, research background of nanotechnology, 10 years of research on nanotechnology here at VNIT Nagpur. So, preparation of nanocomposite, biodiesel production, applications of polymer nanocomposites, and here in nanofluids, where I'm delivering lecture on the same topic in this particular AICTE ATAL platform, that preparation, stability, heat exchangers, in Schillen tube heat exchanger, double pipe heat exchanger, concentric tube heat exchanger, hydrodynamic cavitation, natural convection, forced convection, CHF, critical heat flux that defines the thermal limit phenomena for heat transfer, hydrogen production, solar collector, radiator, wastewater treatment, pharmaceutical applications, CO2 capture. So a lot of applications are revolve around the field of nanofluids. Next slide. Nanotechnology Research Laboratory at Department of Chemical Engineering at Nagpur, we have KD2 Pro that gives you thermal conductivity, resistivity, diffusivity. Then JITA sizer of MOL1 make, DMATA waters, dynamic mechanical analyzer. This is ARG2 rheometer. This is TGDTA system, thermoscientific Hake many lab, and in other lab many equipments are also there. HPCL, GC, GCMH, FTIR. Many things are available in our department. Next. As far as characterization techniques is concerned, this all of you know that XRD, SAME, TAME, TGA, FTIR, EDS, DSC, bed surface analyzer, DLS. So many characterization techniques are required as far as nanoparticle characterization is concerned. Next slide. Importance of heat transfer studies. So applications of heat transfer, buildings to regulate temperature, in cookings because to minimizes the crack, in cookings, refrigeration and drying, in car radiators, and for temperature control in electronic devices. In electronic devices, if you use your mobile phones or laptops, if thermal mismanagement is happen, it may jam, or it can't work properly. If your thermal mismanagement will be happen in your electronic system, then it can't work efficiently. So we need to have a thermal management in the electronic system. So nanofluid is the ultimate solution. This is one. It is also used in solar thermal collectors to convert solar energy to heat and power, and used in thermal controls elements in the aircraft also. In many of these devices, heat needs to be dissipated at a rapid rate, to ensure effective operation and maximum efficiency within the system. As technology evolves, devices have become smaller and thus require better thermal management. Now, if suppose we have a computer, if we have a computer, so we have a fan system, to dissipate its heat. Whatever extra heat is, generated into the system, that can be removed out, or throw out to the atmosphere. But if you are using a very small electronic devices, and if you want the heat to be diffused or heat to be transferred to the atmosphere, what is the mechanism? You cannot apply fan. So nanofluids are pumped at once, which are nanofluids. So around the circuit in a microchanneling way, and it accept the heat and dissipate the heat to the atmosphere around the phone. So if you see always around your phone side, or whatever boundaries of your phones are there, that are always been in a heated format, because it is being transferred through this particular mode from system to the atmosphere, right? So essentially, the more compact of the size, the larger the requirement for effective cooling technology. Therefore, heat transfer enhancement is very important area in thermal engineering, and this is how research into nanofluids began. Next slide. Concept of the nanofluid. What is nanofluid basically? Is a conventional heat transfer fluids have inherent poor thermal conductivity. Okay, so whatever fluids are there, just like water and some other organic materials and fluids were there, ethylene glycol or engine oil, they have very poor thermal conductivity. Can we make it thermally more conducting? Yes, it is possible by incorporating nanoparticles, right? So conventional methods previously for increased cooling rates, okay, कूलिंग करने के लिए या कूलिंग रेट्स को बढ़ाने के लिए previously extended surfaces such as fins, okay, so pin fin, circular fin, helical fins, lot of fin designs were there. It basically increased the surface area to volume ratio of the external surfaces. So protrudement of external surfaces were there, which were indirectly increasing the area at the surface and indirectly increasing the heat transfer from system to the surrounding, right? But the cost of fin was very much too much. We cannot afford, and it is why that alternative technology is there. That is a nanofluid. We can directly pump nanofluid at once, and nanofluid will act as surface area to volume ratio, just like protrudement of the external surface of the things, the increasing flow rate. So if increasing flow rate, previously we increase the pumping cost. So pumping cost will ultimately increase the production cost, and production cost will ultimately increase the product cost. So these two arrangements were a drawback, and that is why there is an alternative technology which is nanofluids. So nanofluids are a new class of advanced heat transfer fluids which is engineered by dispersing nanoparticles smaller than 100 nanometer. Engineer, what is meant by engineer? We cannot add, suppose we take something, clay from outside, and add it into a water. Will it be a nanofluid? No, because nanoparticles are not just added. It should be engineered. Engineered means we should take into consideration its compatibility, whether it is compatible or not. If if you add something into someone, it won't be mixed thoroughly. It won't be dispersed into it. We have to see it carefully. Surface forces, surface tension, physical chemistry. This is very important to consider, take under consideration for having its compatibility. That is why nanofluids are the class of advanced heat transfer fluid engineered by dispersing nanoparticles smaller than 100 nanometers. That we know. In conventional heat transfer fluids, nanofluids are engineered colloidal suspension of nanoparticles, which is in the range of 1 to 100 nanometer in a base fluid, and it is called a nanofluid. Next. So, as far as the preparation of nanofluids is concerned, it don't require a very, hi-fi technology. In the laboratory, we can use our glasswares, beakers, stirrer, magnetic stirrer, or ultrasound probe to have our nanofluids, right? So this don't involve many expenditure. This is a very simple technique. Okay, next slide. So there are advantages and disadvantages of nanofluids, which is to be used in thermal processing unit operations. So high thermal conductivity basically is very important parameter which allow us to use it in heat transfer applications, and heat transfer coefficient at low concentrations of particle appropriate for high temperature thermal processes because of higher thermal conductivity, lower viscosity, and the possibility of designing smaller equipments, because thermal heat management is concerned about, and we can have that thermal management of heat through the smaller equipments also by incorporating nanotechnology or nanofluids into it, cost effectiveness, and needing more pumping cost, to an increase in viscosity in some cases, it is not always, but more pumping power due to increase in viscosity. Actually, viscosity, it is talking about density, because we are adding the very fraction of the nanoparticles, okay, 0.1%, 0.3%, weight by volume percent, 0.4% up to 0.5%. So it is not much more increase of viscosity or density, basically. So it may be omitted, it may be ignored. So, but advantages are always there in terms of nanofluids as far as the heat transfer applications are concerned. Next slide. So causes of instability, we can have many causes of instability. Brownian motion should be there, which is very important parameter, participating in more heat transfer. So we need to critically see it. So if Brownian motion is not good, then that may be a cause of instability. Types of nanoparticles and base fluid. Nanoparticles should be thermally conducting material. This is very important. Sonication time, that will allow us to make the nanofluid stable. So sonication time is also very important, and it may be a cause of instability. Cause of instability matlab, if it is low or not used, then in that sense it has written particle size and particle fluid interaction is very, very important. If it is there, then thermal bridging is the one phenomena which can be taken into consideration for the cause of instability. Thermoporosis. Thermoporosis is a phenomena which is observed in mixture of mobile particle, where the different particle type exhibit different responses to the force of a temperature gradient. So stability can be obtained when the pH value is far from isoelectric point, which is a point of zero potential, thus gives maximum attraction between the particles. And the increase in zeta potential and absorbency increases the stability of the nanofluids. So stability enhances methods are there: addition of surfactant, surface modification technique, pH control of the nanofluid, because stability can be obtained by the pH value, right, is far from isoelectric point, which is a point of zero potential, thus gives maximum attraction between the particle. Ultrasound agitation, as much as you agitate it, it may be in stable form. Then stability enhancement mechanism consequences. Which are the mechanism to enhance stability? Less vulnerable, you know, attractive forces, high electrical double layer repulsive forces, high absorption of ions. High absorption of ions means, enhance the stability of nanofield because high absorption of ions. In which sense? Because the electrostatic stabilization, which absorb ions, can create electrostatic double layer around the nanoparticles, repelling each other and preventing aggregation. So in that sense, I'm talking about high absorption of ions. Then steric stabilization, charge neutralization, dispersion enhancement, reduce vulnerable forces. So this is in terms of high absorption of ions. Dissociation of surface charge particles. This is very important. Dissociation of surface charge particle. Then isomorphic substitution of ions. This is all interlinked with each other as far as the high absorption of ions and all these parameters are concerned. Accumulation of electrons at the surface. And stability evaluation methods are sedimentation, centrifugation method, zeta potential method. As far as zeta potential is the very good stream, we can evaluate directly that the material was stable or not, right? It is the equipment, we have this particular equipment in our laboratory, which is made by the Malvan Jita sizer, that we can evaluate directly by supplying the sample plus 50 minus 50. If we have a curve, we can say that the Jita potential, from the Jita potential, characterization, that the nanofluid is stable. Next slide, please. This Brownian motion, basically, the random molecular movement of a particle is a key mechanism for which the anomalous increase in the heat transport of nanofluid happens. So Brownian motion tends to move the particles from higher concentration areas to the lower concentration areas. And the research shown that the Brownian motion has more impact on the thermal properties of nanofluids than to the effects of a temperature gradient. So I think everybody, we know that the particles is traveling just like a dust particle here and there in the atmosphere. So from one side to the another side, and so it is in stable form and it can transfer the heat. This is very important. Next slide. Effect of sonochemistry. As far as it is concerned, uh, the ultrasound treatment breaks down the large masses of nanoparticles into the smaller clusters or even discrete nanoparticles, right? So sonochemistry treatment is very, very important. Probe type treatment I'm talking about. It can break down the large masses of nanoparticles to a discrete nanoparticles. So sonochemistry के माध्यम से process maintains the stability of colloidal solutions or nanofluids by functionalizing the surface and structure of the nanoparticles, which involves inhibiting the agglomeration of the cluster. With the application of sonochemistry, the diverse nanofluids exhibits variable dispersion behavior, right? So in the first slide, if you see, there are aggregation of the nanoparticles with the help of ultrasound probe of different kilowatts. We can see the hindrance of the nanoparticle throughout the system. So monodispersed nanoparticle after sonication you can see, and this may be used as a means, to stabilize the nanoparticles into the base fluid, and that particular fluid, which is a combination of solid nanoparticles and liquid, referred to as a nanofluid, may be a stable nanofluid. Next slide. Effect of ultrasound on the stability is also equally important, and the ultrasound cavitation generates violent shock waves and micro convection that can break the immiscible binary system. So effect of ultrasound on the stability, if you see that the nanoparticles, agglomerated nanoparticles can dissociate from each other, and as far as if you see its diameter, so with ultrasonication 4.9 and without ultrasonication 5.6 in the right hand side. So this is the case of titanium isopropoxide, water and isopropanol, titanium isopropoxide, water and ethanol, and with various combinations 5, 250 and 25 with sonication and without sonication. So the diameter or the length of the nanoparticle changes drastically with sonication and without sonication. Next slide. The effect of sonication time on the thermal conductivity of the CO, that is copper oxide and water nanofluid. Okay, copper oxide and water nanofluid, we have conducted an experimentation, and it is shown that that using thermal, so everybody will see that how far the thermal conductivity phenomena exist in liquid, because thermal conductivity phenomena is a solid phenomena basically, no? So from particle to particle, heat is being transmitted, without displacement. The particles or the molecules do not displaced from their fixed position. It only impart it heats to the next adjacent molecules because of internal energy. Okay, vibrational, rotational, and oscillations. Because of internal energy, it imparts it heat energy to the adjacent molecule, and adjacent molecule to the next adjacent molecule, and this is going on. And so the thermal conductivity phenomena exist. But in liquid, thermal convectivity phenomena exists, but I'm talking about thermal conductivity because of thermal bridging concept. See, the particle of solid particle of nano and the molecule of liquid, creates a bridging with each other. Then next adjacent molecule of liquid and next particle and next molecule, next particle. Likewise, you can imagine that a bridging kind of system has been formed, and so the heat from one point to the heat from other point is dissipated through this particular thermal bridging concept or phenomena, just like a solid. It acts just like a solid, and it imparts heat from one point to the another point. Hence, the thermal conductivity of CO water nanofluid is enhanced as far as our experimentation is concerned. Next slide. Yeah. So the effect of sonication time on thermal conductivity on of the CO based nanofluid along with the volume fraction. It means, so volume fraction we have added 0.05, weight by volume percent 0.04, 0.02, and here also sonication time is varied for ethylene glycol and for water as a base fluid. So water is a base fluid, monoethylene glycol is also a base fluid. We added CO nanoparticles, and if we incorporated different volume fraction of the nanoparticles, we seen that thermal conductivity value watt per meter Kelvin is drastically improved. Next slide. Because of thermal bridging phenomena. So parameters influencing nanofluid effective thermal conductivity, and that is factors to be considered. Uh, Factors to be considered for improvement of thermal conductivity are the chemical stability is first, thermophysical properties, toxicity which is not applicable for this particular, when you wanted to consume something, or some food grade materials are there, or some enzymatic treatment is there, that time toxicity is very much needs to be taken care. Availability of the nanoparticles, compatibility with the base fluid, and cost is very important. Compatibility means, if suppose if you wanted to insert any nanoparticle into a base fluid, it will floated on the surface, because the liquid won't allow it to get dispersed into it because of surface forces. So this is very important to understand that surface forces kya hai. Surface forces is very important. Surface forces refers to the interaction between particles or molecules at surface of a liquid or solid. I again repeat, this is very important. What are surface forces? Surface forces refers to the interaction between particle of molecule at the surface of a liquid or solid. These forces may play a significant role in determining the behavior of nanofluid, particularly at the nanoscale. So what are the types of surface forces basically? If somebody asks what are surface forces, the surface forces are van der Waals force, weak van der Waals force. So weak intermolecular forces that arises from the interaction between temporary dipoles are van der Waals forces, electrostatic forces, steric forces. These are coming under the surface forces. And so any material, if you combine with any other material, can't allow it to get dispersed into it because of surface forces. So one need to tackle the surface forces, and this is very important aspect, to tackle the stability of the material, nanoparticles into a fluid, because it must be in the dispersible form. Now one should know that what is the difference between surface tension and surface forces. Surface tension is a measure of the energy per unit area at the surface of a liquid. So whenever you add something in the clay made pots, it may absorb the water. It is a result of the intermolecular forces between the molecules at the surface. What are the factors affecting in surface tension? Because this comes under the compatibility of the base. This is very important, because compatibility plays a very important phenomena as far as these two important points are mentioned. Because factors affecting surface tension is a temperature, surfactant. Adding surfactants can reduce the surface tension, and temperature. Surface tension decreases with increasing temperature. This is very important. Surface tension decreases with increasing temperature. Adding surface surfactant can reduce surface tension. Particle size and shape is also play a very important role, because the presence of particle can alter the surface tension. So this is very, very important as far as this particular point, compatibility with the base fluids, is concerned. Next slide, please. Application of nanofluid in energy conservation. Next slide. Energy in terms of heat energy we are talking about basically. So we have conducted so many experimentations in our laboratory, and uh, PhD students have published their papers. They worked uh, on various nanofluids. So they made shell and tube heat exchanger and experimental study of thermal conductivity, heat transfer, and friction factor of Al2O3 based nanofluids they worked on. They have synthesized shell and tube heat exchanger. Actually, this project was supported by DST, and they have provided us 27 lakh grant. So nanofluids will be in tubes, and hot fluid was passed through the shell, and we have seen the effect of the energy exchange, that is heat energy exchange. And we have seen that the heat energy exchange from hot fluid to the cold fluid, that is a nanofluid, which were in the tube, and hot fluid was there in the shell, has tremendously and in a very efficient way exchanged its energy. Next slide, please. So as the concentration of the nanoparticle increases in the base fluid and thermal conductivity value enhances, means concentration of the nanoparticle means volume fraction of the nanoparticles. I have just given you an example of SPF, sun protection formula. So nowadays doctor recommends that 50 SPF cream आप use करो, because to avoid our skin burning from the sunlight, because nanoparticles absorbs the sunlight and repels the sunlight and not allow the sunlight to get past to it. Just like that, concentration of the nanoparticle at certain level I'm talking about, optimization conditions are always there. That increases the thermal conductivity value, that enhances thermal conductivity value, because more the number of nanoparticles, more is the collisions, more is the interaction, more is the Brownian motion into the system, and more is the heat transfer motion which is occurring into the system, and also the internal energy effects, right? So this is the cause and findings, that as the concentration of the nanoparticle increases in the base fluid, the thermal conductivity value is also enhanced. Next slide, please. Yeah, one group, Malika, worked on this ANSYS simulation study of a low volume fraction zinc oxide, copper oxide, and water hybrid nanofluid in a shell and tube heat exchanger, and mesh generated by ANSYS CFD. And this is a schematic view of heat exchanger geometry, where baffles, shell outside, tubes, and shell inside. You can see from one end the nanofluid is supplied. This is the schematic generated via CFD software. Next slide. So the temperature profile of shell and tube heat exchanger against Reynolds number, right? as increased in Reynolds number surely improve the Brownian motion of the particles. Reynolds number, if your velocity of the fluid is high inside the heat exchanger, then Brownian motion is more. Then other interaction of liquid and solid particles are more, and it can interchange or transfer more heat into one another. It can accelerate the rate of heat transfer, and that is the finding, behind this particular ANSYS study also. Results also validated that turbulent flow pattern could transfer more heat effectively compared to the laminar flow. Next slide. Yeah, this figure temperature path lines predicted by ANSYS Fluent also, which is in line with the experimental results which they published. This compares the temperature profile of hot fluid at laminar and turbulent flow conditions using nanofluid and water. So high resistance time in laminar flow reduce the temperature of hot fluid lower than that of the turbulent flow, but with a lower rate of heat transfer. In contrast, turbulent flow facilitated a greater surface area for heat transfer, and the same was found in velocity profile also. As far as if you see the Reynolds number in this particular slide, 17448, that is turbulent region, and here in presence of nanofluid and only by water, the distribution of the heat is something varied. Next slide. This is one of my student findings. He has experimented on double pipe heat exchanger because there are several types of heat exchangers we used to see in process industry. So he run his aluminum oxide based water based nanofluid, and he finds a good findings on overall heat transfer coefficients with Reynolds number. So as Reynolds number increases, the overall heat transfer coefficient, that means the more mass transfer or more heat transfer enhancement, overall heat transfer coefficient Reynolds number for different temperatures, right? So water 2% nanofluids, 3% nanofluids. That means 3% means the nanoparticles of Al2O3 fraction may be varied, and with Reynolds number we have checked and we have seen that there is a increment in overall heat transfer coefficient as far as Reynolds number variation is concerned and the volume fraction variation is concerned. Next slide. Helical coil heat exchanger also we have studied intensified convection heat transfer using zinc oxide nanoparticles in heat exchanger with helical coil geometry at constant wall temperature. So we have also made this assembly. We have made a helical coil heat exchanger with shell and tube arrangement, pumped nanofluid into it, and check the effect of that, how much heat has to be exchanged you know from shell to the tube side of nanofluid and hot water. We've seen that. Next slide. We've seen that the thermal conductivity. Next slide. We see that thermal conductivity ratio, right? That means thermal conductivity of the nanofluid and thermal conductivity of the nanoparticles, with nanofluid and nanoparticles, okay, is that ratio is enhanced with reference to temperature, right? As the concentration of the nanoparticles and temperature increases in the base fluid, the thermal conductivity value is also enhanced, and that is also with reference to 0.2 volume percent of the nanoparticle, that it means weight by volume, 0.3 volume percent of the nanoparticles of zinc oxide based nanoparticles, zero point 0.4 and up to 0.5. So we have come to the conclusion that because thermal conductivity is a temperature sensitive phenomena, if temperature also increases, thermal conductivity value is also respectively increased. Next slide. This is pull boiling, basically critical heat flux instrument we have developed. So it is a heat transfer mechanism which is carrying a phase transition from liquid to vapor, and the enhancement of pull boiling performance using MWCNT, multi-wall carbon nanotubes based nanofluids, a sustainable method for the wastewater and incinerator heat recovery. So this is nanofluid and this is the assembly. So thermocouples are there, data acquisition system is there, and we have made one particular equipment, the CHF, so voltage and current, that both are controlled, so if we increase the voltage and current, so ultimately it it creates a thermal resistance, and the assembly is got heated. So CHF is critical heat flux, which limits the phenomena, thermal phenomena. This is thermal limit phenomena. And on this we have worked and published a 2 3 papers. Next slide, please. So this is a critical heat flux video. If you click that video, it will show you. Please click on that video. Yeah. So you must be seeing that this is nichrome chromium wire with increment of your ammeter, that is current and voltage. So this wire got heated and thermal equilibrium is shifted, and that wire got break. That is a thermal limit point. That is a critical heat flux. Okay. So so different types of wire geometry we have take, and different type of material, different types of surface, rough and smooth surfaces we have used, and we have seen that the surface wettability, the material, and everything works together in this particular to enhance the CHF. Thermal limit enhance करने में काफी काम में है. Substantial deposition of nanoparticles from the heater acts as a bridge between the heater and the surrounding fluids. The bubble formation on the heater surface in case of water as a base fluid, and we have enhanced also the thermal limit of the particular nanofluids by using nanofluids of the particular geometry. Next slide, please. This solar collector. So we have checked that by incorporating micro channels, and one particular assembly has been made. The experiments were conducted from 9 to 4 o'clock. Experiments are run for 15 minutes to attend this steady state experimental condition. Then the value of the outlet temperature is also noted. So this is the topic, and uh, theme of the study was the comparative performance evaluation of fly ash based hybrid nanofluid in microchannel based direct absorption. So we have made a 2 microchannels, but here there is a possibility of having a more microchannels to have a more heat transfer. This was just a testing that whether heat is being transferred into the fluid or not by solar absorption, so solar absorber. So we have created one glass at the top, and we have exposed it to solar. So solar uh, you know radiation accepts it, it gets heated, and we have inserted thermometer at the end. So we've seen that there is substantial heat transfer in between. So here there is a possibility to have a more micro channeling assembly to have a good heat transfer into the system. So this B is insulation of styrofoam block to limit the heat loss. Means whatever heat loss will be there inside the system, that is resisted by this particular insulation which was created with this particular assembly. Next, this is published in Journal of Thermal Analysis and Calorimeter. Yeah, so thermal efficiency of the alumina and fly ash based nanofluid is significantly more. Collector efficiency of the alumina and fly ash, that is 80% alumina and 20% fly ash, to enhance the efficiency, right, is recorded at 72.82%. The addition of fly ash in the alumina hybrid nanofluid decreases collector thermal efficiency. For the silica fly ash based nanofluids, that is, silica is 80 and fly ash is 20, thermal efficiency recorded is 59.23 is achieved. It means there is an enhancement in thermal efficiency when we use 80% alumina and 20% fly ash. So if we have a blend of a nanoparticle, hybrid nanoparticle concept, right? So that one nanoparticles have a good thermal conductivity, another nanoparticle is not having a source of thermal conductivity. We can make it thermally conductance, and we can incorporate that particular system, achieving the property of that particular nanoparticles of which was possessing a good thermal conductivity into this particular ratio, and thermal efficiency in this way have been enhanced. Next. Yeah, solar collector. So this paper is also published, numeric and experimental investigation of Fe2O3 based nanofluids in direct absorption of solar collector. So one of my, you will not believe, BTech students even, have published this paper in Indian Journal of Chemical Society in 2022. Next. Yeah, and this ICEM CFD software is used to build the geometry of the solar collector. मतलब ये जो geometry what we have developed, it was built using the software, it was developed using the software, and also check the verification which we have had in experimentation. Next. So experimental results are compared with the simulation results to check the validity of results, and it is found that the average error is around 8.2. Detailed values and tabulated in this particular one. This is good agreement with the experimental data because some errors are expected due to uneven solar flux. Solar flux मतलब किसी टाइम में सोलर का इंटेंस रेडिएशन आता है, किस टाइम में कम आता है, किस टाइम में ज्यादा आता है. Because of that, that error may be caused. And throughout the experimentation, if you see flow rate wise, the experimental output temperature is depending upon the concentration of nanoparticle is enhances too much. Next slide. So this was about some of the literature survey which is published by my group. So uh, most of the papers are published. Next. So many examples are there, so many applications are there, but I limit the application because the time constraints was there. Next slide. Next slides. So why no applications or limited applications to industry? Because of this stability is a very important phenomena uh, as far as the caping agent. So nanoparticles को चार्जेस को लॉक करना या अल्ट्रासाउंड को बड़े पैमाने पे लेके जाना या उसको स्टेबिलिटी इज द मेन इशू. We cannot say why no applicants, no applicants or industry applicants. We have limited industry applications. So people are working nowadays. I am also working nowadays, to scale up this particular, study and applications to have a permanent stability of the nanoparticles as far as, sonochemistry is concerned. Next slide. So due to enhanced characteristics of nanofluid, a great number of investigations have been performed to study the performance of nanofluid in heat exchanger. Most of the experimental examinations have shown that nanofluid present and enhance its transfer rate in comparison with conventional fluids, and it augments significantly by increasing concentration and Reynolds number. The advantage of applying nanofluids in heat exchangers can vary considerably depending not only on thermophysical properties but also on the geometrical parameters of the heat exchanging equipments and the working conditions. Using nanofluids can provide a vital breakthrough in optimizing the energy utilization. Next slide. Yeah, these two dynamic peoples are there. One is there in SVIT Surat, Dr. Parag Thakur, and one is there in BV Raju. She is applying in NIT IIT. I am hoping that she must be getting selected in future. So next slide. These were my research scholars, who are working all over. And right now, again, 5 research scholars are working in various topics. So next slide. These are the references, and that's all about the application of nanofluid and nanofluid concepts. I must thank all the participants that patiently you heard me, and those who wanted to start research in nanofluids. Tremendous applications are there. If you download research papers through sciencedirect.com, so number of research papers are getting published. I have published 6 books till date, to explore the possibility of the research in the field of nanofluid, various applications in electronic, in various applications are there. You just try downloading the papers, you will see a numerous applications and scope out of it to work. And the beauty of this particular nanofluids application in heat transfer and in other one is that in medical also there are a number of applications that you can start new research, and the publication rate in this particular nanofluid application research is more. Acceptability of the research paper, is more in this particular field. So I hope that many of you must have been motivated, through this particular application of nanofluid and start your at least small research at your laboratory and have the effects of nanofluid into various applications. Next slide. So I again thank Dr. Shailesh and Dr. Utkarsh for inviting me on this particular platform of ATAL. Thank you. Yeah, over to you, Dr. Shailesh.
Yes, thank you, sir, for such a nice, wonderful session for our participants. Now, I request the participants, if you have any question, the forum is open.
If any question is there, I can answer them.
Sir, may
Yes,
I
please
ask
go
the
ahead.
question?
Yes, yes, you please go ahead.
First of all, thank you very much, sir, for the wonderful presentation, most technically spoken presentation among all these sessions what are going on. And also, all thanks to those research scholars who have worked under your guidance. And such kind of research activities keep going on with innovative ideas. And, sir, in these nanofluids, to what extent or what level the stability of the nanofluids, the quality of the nanofluid can stay stable in under very high temperatures, like you are going, for example, in a petroleum industries, they are digging up these drills where they use these nanofluids to remove the heat. Will to what extent of temperature it can withstand?
Yeah, this is very good question. Basically, uh, actually, this is a nanofluid, exchange phenomena. Exchange means the base fluid which don't have thermal conductivity or thermal conductivity application. We enhance that application basically by incorporating thermally conducting property nanoparticles into it. Then we combine and we call it as a nanofluid, and that nanofluids together gives effect. So it is depend that how much heat it is exchanging into it. It is basically used as a coolant fluid basically. Nanofluid is used as a coolant fluid. So whatever, suppose in the bike you must have a that particular where you are inserting oil, so it gets heated. It's so viscous is there, so protrusion is there external surfaces. So विस्कस ऑयल्स का एक पर्टिकुलर एप्लीकेशन होता है. It takes time to get heated, it takes time to cool. So instead of going by designing a very rigorous system of fin or arrangement, we can have a direct nanoparticles. The effect is to have a greater heat transfer area into the base fluid and exchange the heat. So basically the purpose is to exchange the heat to get it cooler faster basically, right? So get it cooler faster. That is the very important concept I'm talking about. So it is also depends upon how much fraction nanoparticles to be added. So if you add more than certain limit nanoparticles into it, it may also tends to agglomerate to each other and can minimize the heat exchange into the system. So this is all aspects. So we cannot directly tell that this temperature we can achieve, this temperature we can achieve. We have achieved a certain temperature in by performing experimentation into the laboratory, that nanofluids can be used as a coolant to exchange the heat from the outside. If it is heated, then for heating purpose also nanofluid is heat, because it enhances the heat, again heat transfer again by heating, because it exchanges heat by the heating. So in this way we can think about this particular nanofluid in the heat transfer research.
Correct. One quick question, please, because we have to run to the next presentation. Any one question we can take now?
You can give my email ID to all the participants,
Yes, sir. Yes, sir.
so that if anyone wanted to connect me by email or by my telephonic conversation, if any queries will be there, I will be happy to
Yes, sir. Sure,
resolve
sure.
their queries in online mode also, by direct conversation also.
Yes, sir. Correct, correct. Great. Yes, any quick question? If you have any question, then we can continue. Otherwise, we have next session immediately going on.
Sir,
Okay.
I have one question.
Yes, sir, please.
Sonawane sir,
Yeah.
if you are using nanoparticle, so what about pressure drop? It is increasing or it will increase, na, sir?
It depends. If suppose you know the number of nanoparticles you added have a greater gravity, you can say a density into it, so it actually increases, but not at great level, so that we can have a cognizance of it basically. So while running the nanofluid into a heat exchangers, shell and tube, double pipe heat exchangers, helical shape of heat exchangers, spin fin. So in this particular one, we observe that the pressure drop can be ignored, not increase so much that our operation, slow down or stops in exchanging the heats from hot to the cold like that. So it is ignored basically.
Okay, thank you.
Now I request Umesh sir to continue with the vote of thanks.
Thank you, Shaili sir. It gives me immense pleasure to deliver the vote of thanks for today's insightful session. First and foremost, I would like to thank our esteemed speaker, Dr. Shriram S. Sonawane sir, for his valuable insights and for sharing his extensive knowledge with us. We appreciate the time and effort you put into preparing such a comprehensive and engaging presentation. Thank you, sir. To our attendees, thank you for your active participation and for taking the time to join us today. We hope you found the session as informative and engaging as we did. In closing, we are grateful to everyone who has been a part of this event. Thank you once again and have a great day. Thank you, everyone.
Thank you,
Thank you, sir.
Shailesh.
Thank you
Let's
so
meet
much.
again. Bye
Thank
bye.
you. Thank you. Yes. Participants, important announcement to you. You are supposed to join the session immediately. The link is already posted onto the WhatsApp group. Thank you. Thank you so much. Thank you, sir. I'm
Thank you.
turning
Bye
off the
bye.
mic.
Bye bye.
Thank
Bye
you.
bye.
Thank you.
I will leave now. Okay.